Imagine a night of profound stillness far from the glow of our towns and cities. The air is crisp and cold. Above, the stars are scattered like diamond dust. Then something extraordinary begins to happen. A faint, ethereal glow appears on the horizon, unassuming at first, like a distant cloud catching an unseen light. But this is no cloud. It grows. It brightens. It begins to move with a silent, otherworldly grace. Great ribbons of luminous green unfurl across the heavens, shimmering and swaying like celestial curtains. This breathtaking spectacle is known to science as the aurora. For millennia, humanity has looked up with awe. Ancient cultures wove elaborate myths, spirits of ancestors. The fury of gods, a bridge to the afterlife. It is a phenomenon that seems to defy our earthly experience, a silent fire that burns without heat, high in the upper atmosphere. Today, while we have unraveled the scientific processes, the sense of wonder it inspires remains. The aurora is a visible manifestation of the deep connection between our planet and the sun. It reminds us we live on a world constantly interacting with cosmic forces. These lights have two names, depending on where you see them. In the northern hemisphere, the Aurora Borealis, the northern lights, Aurora. The Roman goddess of the dawn, Boreas, the Greek god of the north wind. In the southern hemisphere, the Aurora Australis, the southern lights. Australis, Latin for southern. Despite different names, they are mirror images, twin displays at opposite ends of our world. The experience of standing beneath an active aurora stays with you forever. The sheer scale is almost impossible to comprehend. The lights can stretch from one horizon to the other, at times gentle and slow, a soft, diffuse glow that paints the darkness with subtle hues. At other times, astonishingly dynamic. Bright, sharp rays that shoot across the sky, intricate spirals that twist and pulse with frantic energy. In those moments, the sky truly feels alive, a vast, vibrant canvas upon which the laws of physics are painting a masterpiece. The story of the aurora does not begin on Earth, but rather 93 million miles away, at the heart of our solar system. It begins with the sun. Our star is not a calm, steady ball of fire. It is a fantastically turbulent and active sphere of superheated plasma. Its surface churns and boils, and from its outer atmosphere, the corona, it constantly ejects a stream of charged particles. This continuous outflow, composed mainly of protons and electrons, is known as the solar wind. It is a kind of stellar breath, flowing outwards in all directions, sweeping past all the planets in our solar system, including our own. It is the fundamental ingredient required for an aurora to occur. This solar wind travels at incredible speeds, typically around 1 million miles per hour, though it can be much faster during periods of heightened solar activity. It carries with it not just particles, but also a portion of the sun's own magnetic field, the interplanetary magnetic field. The journey from the sun to the Earth takes, on average, 2 to 4 days. For most of that journey, these particles travel through the vast emptiness of space. But as this stream of solar plasma approaches our world, it encounters a formidable obstacle, Earth's own magnetic field, an invisible force field that surrounds our planet and shields us from the harshest effects of this constant cosmic bombardment. The intensity of the solar wind is not constant. The sun goes through cycles of activity, the most well-known of which is an approximately 11-year cycle. During periods of high activity, known as the solar maximum, the sun's surface is often marked by sunspots, and it is more prone to producing powerful eruptions. These eruptions, such as solar flares and coronal mass ejections, can hurl vast, dense clouds of plasma into space. When a coronal mass ejection is directed towards Earth, as the solar wind races towards Earth, it encounters our planet's first line of defense, the magnetosphere. This is a vast, invisible bubble generated by the movement of molten iron in Earth's outer core. The magnetosphere extends tens of thousands of miles into space, and its primary role is to deflect the majority of the charged particles that make up the solar wind. It acts like a rock in a stream, forcing the flow of particles to part and sweep around our planet. This protective shield is absolutely essential for life on Earth, as it prevents the solar wind from stripping away our atmosphere and bombarding the surface with harmful radiation. However, the magnetosphere is not a perfect, impenetrable sphere. On the side of Earth facing the Sun, it is compressed by the force of the solar wind. On the night side, it is stretched out into a long, teardrop-shaped tail, known as the magnetotail, which extends for millions of miles away from the Sun. More importantly, the magnetic field lines that create this shield are not fully closed. At the North Pole, the field lines curve downwards and connect back to the planet, creating a funnel-like polar cusp. At the South Pole, the field lines curve downwards and connect back to the planet, creating a funnel-like polar cusp. It is here, in these specific areas, that the shield has a vulnerability. These polar cusps act as gateways. Instead of being deflected, some of the charged particles from the solar wind can become trapped within the magnetosphere and are then funneled along the magnetic field lines down towards the Earth's upper atmosphere. They are guided with incredible precision towards two oval-shaped regions surrounding the magnetic poles, the auroral ovals. This is why auroras are typically seen only in high-latitude regions. The magnetic field acts as a cosmic focusing lens, collecting particles from a vast area of space and concentrating them into these relatively small zones above the Arctic Circle and above the Antarctic Circle. The interaction between the solar wind and the magnetosphere is highly complex and dynamic. As the solar wind pushes and pulls on the magnetic field, it can cause the magnetotail to stretch and then suddenly snap back, a process known as magnetic reconnection. This event can powerfully accelerate trapped particles and fling them back towards Earth's night side, injecting a huge amount of energy into the auroral ovals. This is what often triggers the most spectacular and active auroral displays, known as auroral substorms, transforming a gentle glow into a vibrant, fast-moving spectacle that can fill the entire sky. Once the charged particles from the solar wind have been guided by the magnetosphere down into the upper atmosphere, the final and most visible part of the auroral process begins. These particles, primarily electrons, enter the atmosphere at tremendous speeds, carrying a great deal of kinetic energy. Here, between 60 and 600 miles above the Earth's surface, the air is incredibly thin, but it is not empty. It is composed of atoms and molecules of gas, principally nitrogen-oxygen. The creation of the aurora is the result of countless high-energy collisions between incoming solar particles and atmospheric gases. When a fast-moving electron collides with an oxygen atom, it transfers energy to that atom, excitation. The oxygen atom absorbs the energy, and one of its electrons jumps to a higher orbit. That excited state is unstable. The atom can't hold the extra energy, so to return to stability, it must release it. It releases a tiny packet of light, a photon. The aurora is the combined light from trillions of these emissions. Think of it like striking a bell. The collision is the strike, giving energy to the bell. The ringing is the bell, releasing energy. For the aurora, the ringing is light, not sound. Each collision makes a single, fleeting point of light. When billions of collisions happen every second across a vast area, our eyes see a continuous glowing curtain or an arc of light. The aurora is a natural, large-scale neon sign. Brightness depends on particle density and particle energy. A gentle stream makes a faint glow. A powerful surge, like a coronal mass ejection, increases collisions per second dramatically, producing a brighter dynamic display. The atmosphere becomes a vast screen, and the solar wind acts as the projector, painting the sky with light from these atomic interactions. One of the most captivating aspects of the aurora is its rich and varied palette of colors. While green is the most common color we associate with the northern and southern lights, displays can also feature beautiful reds, pinks, blues, purples. These different colors are not random. They are a direct result of the specific physics of the particle collisions. Two key factors determine the color of the light produced: the type of gas atom being struck, oxygen-nitrogen, and the altitude at which the collision occurs. Each combination produces a unique wavelength of light, which our eyes perceive as a different color. At this height, the concentration of oxygen is optimal for producing this specific wavelength. Our eyes are also most sensitive to this part of the spectrum, another reason green is most commonly reported. When you see those classic shimmering green curtains, you are witnessing excited oxygen atoms glowing in the middle layer of the auroral zone. Higher up in the atmosphere, above 150 miles, collisions with oxygen can produce a different color, a deep, haunting red. At these extreme altitudes, the atmosphere is far less dense. An oxygen atom that has been excited here can remain in its energetic state for up to 2 minutes before it finally releases its photon of red light. Because the atmosphere is so thin, there is less chance of it being deactivated by another collision before it has time to glow. These all-red auroras are rarer, usually seen during intense solar activity, often appearing as faint, high-altitude fringes above the main green display. The blues and purples in the auroral palette are the work of nitrogen, the most abundant gas in our atmosphere. When solar particles strike nitrogen molecules at lower altitudes, typically below 60 miles, they can cause the nitrogen to emit blue light-violet light. Often, you will see a purplish-pink fringe along the lower edge of a particularly bright and fast-moving green curtain. This is caused by highly energetic particles penetrating deeper into the atmosphere and colliding with nitrogen molecules. The beautiful mix of colors in an auroral display is therefore a vertical map of the atmosphere's composition, painted by the energy of the sun. The aurora is not just a static glow. It is defined by its movement and its ever-changing forms. Scientists classify auroral displays into several distinct types. The simplest and often earliest form is a quiet arc, a smooth, gentle band stretching east to west. It can remain stable, a soft, luminous bow against the stars. Multiple parallel arcs can form like celestial stripes. As activity increases, arcs transform into auroral curtains, drapery. Curtains hang like vast, shimmering fabrics. They have defined vertical structure, many fine parallel rays. The rays align with Earth's magnetic field lines. That movement makes curtains look like they're waving or folding. Motion can be slow and graceful, or it can be rapid and dramatic, with ripples racing along the curtain. At substorm peak, the display can culminate in a corona. A corona occurs when the aurora is directly overhead. Vertical rays appear to converge to a single point above the observer. The result is a starburst-like explosion of light. Coronas are dynamic, pulsing and shifting in shape and color. The aurora can also appear as diffuse patches that flicker or pulse, or as swirling spirals that twist across the sky. The exact shape and motion are dictated by magnetospheric conditions and incoming solar particles. The flow of energy isn't smooth and uniform. It's lumpy and turbulent. Those variations create intricate structures and movements. No two displays are alike. Each night is a unique performance. Witnessing the aurora is a goal for many travelers, but success depends heavily on being in the right place at the right time. Best viewing locations lie within the auroral ovals. These are rings around the Earth's geomagnetic poles where the lights concentrate. In the northern hemisphere, prime viewing starts with northern Alaska, Yukon, Northwest Territories, Nunavut, Iceland, Greenland, northern Norway, northern Sweden, northern Finland. In these places, the aurora can be a near-nightly occurrence during the darker months. In the southern hemisphere, the Aurora Australis is much harder to see. The auroral oval is centered over Antarctica and the surrounding Southern Ocean. There are very few accessible land masses within that zone. The southern tip of South America can occasionally see the lights. The southern tip of Australia can too. Tasmania, New Zealand. Mostly consistent viewing of the southern lights is for scientists in Antarctica, or the fortunate few on ships. Timing is just as crucial as location. The most important requirement is darkness. That means the auroral season in high latitudes runs roughly from late August to early April in the north. During summer, these regions experience the midnight sun, so the sky never gets dark enough for auroras. The best time of night is typically between 10 p.m. and 2 a.m. local. Auroras can happen anytime in the season, but frequency and intensity are often highest around the March and September equinoxes. That's a geometric effect from Earth's tilt, allowing more efficient transfer of solar wind energy into the magnetosphere. The sun's roughly 11-year activity cycle also plays a big role. Around solar maximum, geomagnetic storms are more frequent and powerful, producing intense auroras that can reach lower latitudes. Seeing the aurora is often a game of patience and preparation. Following a few key principles can greatly increase your chances of success. The first and most critical step is to escape light pollution. The faint, delicate light of the aurora is easily washed out by the glow from streetlights, buildings, vehicles. You must find a location as far away from city and town centers as possible. A remote park, a countryside road, a lakeside cabin can be an ideal spot. The darker your surroundings, the more detail and color your eyes will be able to perceive in the sky. Next, you need a clear sky. Clouds are the aurora hunter's greatest enemy. They sit much lower in the atmosphere and will block your view of the lights above. Before you head out, be sure to check the local weather forecast for clear conditions. Even a partly cloudy sky can obscure a display, so the clearer, the better. It is also wise to check the phase of the moon. While a full moon can beautifully illuminate a winter landscape, its bright light can also diminish the visibility of a fainter aurora. The darkest nights during a new moon offer the best contrast. Modern technology provides an invaluable tool for aurora chasers, the Aurora Forecast. Several websites and smartphone apps provide real-time data and short-term predictions for auroral activity. They monitor solar wind speed, solar wind density, and the orientation of the interplanetary magnetic field, using this information to predict likelihood and intensity. These forecasts often use a KP index, a scale from 0 to 9 that measures geomagnetic activity. A higher KP number means a stronger storm and a greater chance of seeing the aurora, potentially at lower latitudes. Checking these forecasts can help you decide if it is worth heading out on a given night. Finally, be prepared for the conditions. Auroras are most often seen on cold, clear nights. It is essential to dress in warm layers, including insulated jacket, insulated trousers, thermal underwear, warm socks, boots, hat, gloves. Waiting for the lights to appear can involve standing or sitting still for long periods in freezing temperatures. Bringing a warm drink in a thermos and perhaps a portable chair can make the experience much more comfortable. Patience is the ultimate virtue of the aurora hunter. The lights operate on their own schedule. A spectacular display can erupt with little warning after hours of waiting under a quiet sky. Beyond the captivating science, the aurora holds a rich cultural and historical significance. For countless generations who lived without a scientific explanation, these celestial lights were a source of powerful myths and legends. In Norse mythology, the aurora was believed to be the Bifrost Bridge, a shimmering, fiery archway, Midgard-Asgard. Reflections from the shield's armor of the Valkyries, Valkyries who decided the fate of warriors in battle. These stories imbued the lights with a sense of divine power and cosmic importance. In North America, indigenous peoples had diverse interpretations. The Cree saw the lights as the spirits of the dead dancing in the sky. The Inuit believed the lights were the souls of their ancestors playing a game with a walrus skull. These legends often came with rules of conduct. It was sometimes considered dangerous to whistle at the aurora, as it might cause the spirits to descend and carry you away. These beliefs highlight a deep spiritual connection to the natural world. Even today, with our detailed scientific understanding, the aurora continues to surprise and inform us. Auroras are not unique to Earth. Observed on other planets with an atmosphere and magnetic field. Jupiter, Saturn, Uranus, Neptune. Studied by telescopes like Hubble, extraterrestrial auroras help scientists understand atmospheric conditions and magnetic environments. The aurora is a vital tool for studying space weather, changing conditions in space that affect our technology. Satellites, GPS, power grids. To witness the aurora is to connect with something ancient and immediate. Stand where our ancestors stood and feel wonder at the sky's silent, luminous dance. A humbling reminder of our planet's place in a vast, dynamic cosmos, immense forces producing moments of fleeting beauty. If you find yourself under a clear, dark sky in the far north or south, look up. You may see the magic, solar energy made visible, and a memory that will illuminate your thoughts for a lifetime.